Hi, Alessandro Rudi. Optimal kernel methods for large-scale learning.
Let me turn this on.
So, good morning, and I would like to thank the organizers and you all for this fantastic workshop. So, today I'm going to speak about the second part of the work I did with Lorenzo on how to scale up kernel methods to deal with large-scale machine learning problems. This work is together with Lorenzo and Luigi Caratino, our PhD students. And so Lorenzo, in the first part, analyzed statistical and computational properties of data-independent features. In this second part, I analyze statistical and computational properties of data-dependent features, very simple kind of data-dependent features, showing that they can achieve, be useful to achieve lower computational complexity while still retaining optimal statistical properties for kernel methods. In the end of the talk, I will show that it is possible to exploit specific properties of such data-dependent features in order to make the learning algorithm even faster. So, we are in the standard supervised learning problem. We have a distribution that is fixed but unknown, and our goal is to learn the function that minimizes the excess risk, so the expected risk with respect to the distribution on a space of function that we choose, h. As I say, the distribution is unknown and we access it only through independent samples drawn from it. In this talk we will consider the square loss in the expected error. So, in the first part of the talk, I will introduce kernel methods, recalling their statistical and computational properties, and they will be used as reference for the other two sections, where I introduce and analyze the data-dependent features, giving the statistical, analyzing their statistical guarantees, and then I will introduce our algorithm. So here we have a kernel, and H in this case is the function space induced by the kernel, so it's reproducing kernel Hilbert space. The problem here is very a classical example of empirical risk minimization. Indeed, we minimize the empirical error on the observed data plus a suitable regularizer. In this case, the Tikhonov regularizer. Here, H is exactly the reproducing kernel Hilbert space induced by the kernel. So, this is a very well studied algorithm. I will recall its properties. So, by giving very basic assumptions on the distribution of the output with respect to the input, and so we are asking it to be sub-exponential, the kernel to be bounded, and there exists a solution for this problem. We have optimal learning bounds, so this is the standard results from 2005. Under the assumption above, we have the classical bias variance decomposition. So we see that if we optimize here in lambda, this is the regularization parameter, the algorithm achieves a learning error that is in the order 1 over square root of n. So in the same paper, it is proven that it is minimax optimal.
So here, when you write this twiddle, you always hide the dependence on the space, right?
Exactly. The dependence on the space depends on the, on the kernel you choose. Okay. So if you choose, for example, linear kernel, okay, here you would have the dimension, exactly the dimension. Otherwise, it depends on the specific kernel you decide to use. You can do better than that, so by adding refined assumptions. You have seen already them in Lorenzo's talk. Everything is around the L, it is the integral operator associated to the kernel. We define the effective dimension of the kernel. It is, in a sense, a way to measure the effective degrees of freedom of this problem. And we assume that it depends on this parameter gamma between 0 and 1, and it's essentially a way to control the eigenvalue decay order of the operator L. So if gamma is close to 0, the problem is finite rank. If gamma is 1, it is a no assumption, since it just recovers the basic case we have seen before. And the same for the source condition. Here we control how fast the coefficients in representing the function fh with respect to the eigenbasis of L go to 0. So if r equal 1/2 is just asking that fh exists. With r going to infinity, we are saying that it can be represented with a finite number of eigenvectors from the eigen decomposition of L. So with these two assumptions, we obtain better rates actually, and by optimizing them, so indeed you see that the variance term now depends on the capacity condition and the bias on the source condition. By optimizing lambda, you see that we can achieve even better rates. Indeed, if gamma is close to 0 or r very big, it is n to the minus 1. So this is the reference. What we are going to do in the next of the talk is to show that by using a right number of data-dependent features, we can achieve the same bounds, but saving a lot of computation. Okay, so what happens from a computational viewpoint, and why kernel ridge regression cannot be used on large-scale data sets? The problem we have seen before can be solved in closed form via the representer theorem. Indeed, the function, the estimator is a linear combination of the kernel functions computed on the observed examples, and the coefficients of the linear combination are the solution of this linear system, where k is the so-called kernel matrix. So it is an n times n matrix. N is the number of examples we have, and each element is just, so the element ij is the kernel function computed on xi, xj. To solve this linear system, you need obviously to compute this. So if you want to solve it via direct methods, you have to compute the matrix and to invert it. So it requires n square evaluation to compute the matrix, n square in space to store it, and cube in time to invert. Obviously, if you have data set with millions of points, you cannot do it. So the question is, can we have an algorithm that is still non-parametric, that has the same statistical properties of kernel ridge regression, but which is way faster and with less memory footprint than this one? Okay, so here I recall the model is the number of kernel function of the linear combination of the final estimator, and as I said, n square in space, n square kernel evaluation, and cube in time. So the idea of random projections, it is very simple and consists in solving the problem we have seen before. Instead of solving it on H, we solve it on a subspace of H, in particular Hm. Here Hm is the span of the kernel functions computed on some points. We call them, let's say, Nystrom points, and we sample them uniformly from the data set. So we choose M, hopefully way smaller than the number of points of examples. We sample them from the data set, we build H, and we solve this problem. In practice, it boils down to sampling some columns from the kernel matrix and solve this smaller problem. So here the estimator, since Hm is defined in this way, is the linear combination of kernel function evaluated on the Nystrom points. So just to be clear, we consider the empirical error over all the observed examples, but the estimator is expressed with respect to the Nystrom points we have selected. In this case, the coefficients are given by the solution of this system. So, in a sense, we have to compute, we have to solve this linear system. Note that these kind of techniques are known with different names. So, in the statistical machine learning setting, it is known as Nystrom method, and it is from 2000. In Gaussian processes, you can find it as inducing inputs or pseudo inputs. You have something similar in randomized linear algebra, where it is just this thing, so column sampling. You want to solve this big linear system, the one with dot line, and you want to save computation, so you do a kind of randomized subsampling of the problem. In that specific case, note that the goal is different, because in statistical learning, we want to minimize the excess risk of our estimator with respect to the best possible function. In randomized linear algebra, we want to find the solution of this problem, that in our case is just the empirical problem. Okay, so what is the computational cost of solving this? We have to, so I didn't say what is KMM here. So KNM is the matrix you build by doing this kind of column subsampling of the right kernel matrix. KMM is just the first part of this matrix. So the kernel matrix you obtain by computing it only on the Nystrom points. So it is of dimension m times m. So the total computational cost of solving this problem is an m kernel evaluation, so to compute this matrix, nm square to compute this matrix and to invert it. And it requires an mn space, since you can just compute this product by blocks, and you need just m square in space to store this matrix and to invert it. Okay, so if m is smaller than n, we have a real computational gain. Otherwise, it is just as kernel ridge regression. On the other hand, we see that if we put m equal n, we have just kernel ridge regression. So at least in this case, it has optimal statistical properties. So it is possible to have both optimal statistical properties and a number m that is smaller than n. This is our result here. We show that we have this result, it is under the same basic assumption of kernel ridge regression. We have the same bias variance trade-off plus an additional term that we call computational error. And by optimizing them, you see that you achieve the optimal learning rate of 1 over square root of n if you select lambda as usual, so 1 over square root of n, and the number of Nystrom points of 1 over lambda, so square root of n. So the consequence of that is that a number of Nystrom points in the order of square root of n is enough for optimal generalization, at least in the worst case scenario. So as I said, it matches the minimax lower bound of the sum of kernel ridge regression, and it covers the case of some well-known case. For example, if you choose wisely your kernel, you are covering the case of Sobolev space with S slightly bigger than d divided by 2. On this topic, the previous results cover the case of fixed design setting. So this is the first result on random design setting that shows this behavior. We can do better than that by considering the refined assumptions, and we have here the same terms. Here, so the variance consider the capacity condition, the bias, the source condition, and again we obtain the optimal learning rates that now depend on R and gamma. I didn't say before, but here you have lambda that depends on this parameter that in principle are unknown, since you have access only to your examples, but you can find it via cross-validation. It is possible to prove that via cross-validation you find the lambda that has the same optimal properties as this one. If you remember, in Lorenzo's talk we achieved a similar result with random features, and you cannot see the difference in the worst case scenario, but here you can see that you need a number of Nystrom points that is smaller than the number of random features to achieve the optimal learning rate. Indeed here, so let's assume that we need a number of features that is like n to the c. Here I show the exponent c with respect to Nystrom, and the exponent c if we use random features. So red, yellow is worse than blue. You see that the exponent for the random features with respect to the parameter r and gamma is smaller than the one of Nystrom is smaller than the one of random features. They have still similar behavior. Indeed, they work very well in this region, and this is the simplest region if you want. So they work well with respect to the sparsity of the problem. I mean with sparsity the fact that the function that we want to learn is well represented with respect to the basis of the linear operator, of the integral operator. Not very well with respect to the fact that the linear operator could be finite rank or with a small effective dimension. This problem can be solved, as we have seen for random features, by using adaptive sampling, and indeed in our papers we covered the adaptive sampling case, but here I'm not going to speak about this. I will cover more the optimization aspect, as we will see later. So what do we gain here? So first of all, the model now, since it is expressed with respect to the Nystrom points, it is only of square root of n elements. To compute the whole problem, we need n squared, so n in space, n square root of n kernel evaluation to compute the matrix k and m, and now only n squared in time. That is nm squared, m is equal to square root of n. So we go from n cube for kernel regression to n squared. In the rest of the talk, I'm going to show that we can do even better than n squared. We can do n square root of n by exploiting specific properties of the Nystrom points. And this is our algorithm with update Falkon. Okay, so for the Nystrom problem, we have to solve this linear system. If you want to solve this linear system with direct methods, you have to, the bottleneck is to compute this product that requires nm squared in time. So a standard way to avoid this problem is to solve it, for example, via first order methods. Okay, in this case, you would need just nmt, where t is the number of iterations you do, but note that the cons of this approach is that the number of iterations depend on the condition number of this matrix. And since here we have this term, so lambda kmm, the condition number of this matrix can be unbounded, because there is no reason, so even if it is positive definite, there is no reason why the smaller eigenvalue of kmm should be bigger than something. What we decided to do is to precondition this problem. If you precondition a problem, I just recall a few things. You find an equivalent linear system from which you can recover the original solution, but such that the matrix has a condition number that is close to 1. Ideally, assume that we choose the matrix P such that PP transpose is equal to the inverse of H. When you solve this linear system, you go from a number of iterations that is proportional to the condition number of H to a number of iterations that is 1. Obviously, you don't want to use H to the minus 1 because it is equivalent to solving the original problem. So the question is, how can we find a good preconditioner? Because in general, it can be an hard problem. So I want just to note that this approach has been used, but to solve the problem of kernel ridge regression. So in kernel ridge regression, where the matrix you want to precondition is this one, they used Nystrom points to find a good preconditioner for this matrix. The cost they incur in doing that is nm squared. So their algorithms cannot go faster than n squared in the end. Here we go up to n square root of n. Okay, so our idea is to exploit the statistical properties of the Nystrom approximation to find a good preconditioner. Why? Because let's start from this consideration. If we let the number of points to be equal to the number of random features of Nystrom points, what you have here is that these two match. So it is the ideal preconditioner we would use. That is just the inverse of this matrix. While in practice we consider this preconditioner, and if you see that, first of all, if n is equal to m, these two matrices are just the same. What we prove is that statistically, a number of Nystrom points that is way smaller than n is enough to give the same spectral properties of these two matrices. I can give some more hints, considering that if you see here we have a sum of two terms. The second term is the same, and in a sense tells you how many eigenvalues and eigenvectors of the whole matrix you want to approximate. Because any eigenvalue that is bigger, that is smaller than lambda times the largest eigenvalue of KMM is not really useful to approximate it, since it is covered by the regularization term. So what we have to prove is that these the first eigenvalues up to lambda of this matrix are well approximated by this other matrix. Okay, so what we do, our algorithm, we call it Baby Falkon, it consists just in computing the preconditioner and then to do precondition gradient descent. So it is as before, but here we put the matrix P where it should be. Actually, the true algorithm, instead of using gradient descent, we use conjugate gradient. Why? First of all, because it is fastest, and then because we don't have to compute to find the parameter, the step parameter, and then we find a cheap way to compute the preconditioner P by using two Cholesky decomposition. So it requires m cube to compute P. Okay, so let's analyze the statistical properties of this Falkon algorithm. So we have the three terms we have observed in Nystrom kernel ridge regression, plus an additional term that is a negative exponential. It depends on the number of steps, and a term that depends on lambda and m. So if you optimize lambda, m, and t here, you see that if you take lambda as usual, 1 over square root of n, m here it is slightly bigger than before. We have a logarithm factor more. So log n divided by lambda, and t only log n, you achieve the optimal learning rate of 1 over square root of n. So it is interesting because m is essentially the same as before, but here we have proven that we just need a number of steps that is logarithm of the number of examples. No hidden factors, it's just log n. And you can see here, if you put the things inside. More generally, if we add the refined assumptions, in the same way we achieve the optimal fast rate, but still by using a number of of iteration that is a logarithm of the number of examples.
When you do the approximate preconditioner, then you have the condition number of this matrix that you invert, isn't it of order 1 over lambda?
I will show you. I will show you later.
I just wonder whether this shows
It is exactly. I will show that the preconditioner is the condition number is bounded by the inverse of this quantity. Okay, so if you choose m big enough, it is a constant. In particular, I choose exactly m in the order of 2 times log n over lambda. So it is controlled by 2. Okay. So here I was just to recall some relevant works on this topic. One is the random features with kernel ridge regression that Lorenzo analyzed last time. There are other algorithms like divide and conquer, nitro, or why not solving Nystrom with SGD. Okay. All these algorithms achieve, at least for the basic case, a computation that is in the order of n square. And so the comparison is that from considering the space, we use the same space, that is n, the number of points. But we have much smaller computational complexity. Since those algorithms are in the order of n square, we are in the order of n square root of n. Okay, so just to give an insight of the proof, we can, if you want, we can organize it in 2 lemmas. In one lemma, we bound the excess risk of our estimator, of Falkon estimator, with respect to the excess risk of Nystrom kernel ridge regression, plus a term that depends on the optimization. And indeed, it is just the so exponential minus the number of iterations divided by square root of the condition number. It is interesting because here, I mean, it is not just so while the results for the optimization are in the H norm, so the norm of the matrix H, here the problem is in terms of the excess risk. So it is interesting. It can be even generalized to other optimization algorithms. And then the second lemma, as we were saying, is to control the condition number of the conditioned matrix. And here we prove that the condition number is controlled by this quantity, and if you choose m big enough, it is smaller than a constant. So it does not depend anymore on lambda, m, and n. So finally, we have proven that square root of n random features are enough, and a number of iterations is log n is enough for optimal generalization. If we compute the computational time, then we have still square root of n for model, n in space, and n square root of n for kernel evaluation, but now we go from n square in time to n square root of n. And to our knowledge, this is the first algorithm that requires n square root of n in time. and still has optimal statistical properties. Okay, so now some experiments. Since we claim that it is so good for large-scale learning problems, let's do it on a large-scale learning problem. It is the Higgs dataset, the one they used to find the Higgs boson at CERN. It has 10 million examples. So we choose M, the number of Nystrom points, 50,000, and we run different algorithms on this dataset. So here you can see the Falkon. So here you have the number of iterations of epochs if you use SGD, and here the mean square error. You see that Falkon after 7 iterations achieves the optimum, the smallest. The MSC is on the test set. And then we compared for some algorithm, you know, so it is Nystrom plus SGD, okay? Then you have Nystrom plus GD. You have Nystrom plus, okay, so which one is that? So Nystrom plus the CG, okay? So you see that if you use conjugate gradient, you need at least 10 times more iterations to achieve the same result. Let's do it more generally on other data sets. So here we compared some results in literature on other algorithms for large-scale learning problems. We did this analysis. So let's say Luigi did this analysis on his workstation under his desk. It is a workstation with 6 CPUs and only one GPU. I want to say that because the other results are obtained using clusters. For example, here, this one, where is this? So these results are obtained with a cluster of 128 machines. Okay, so even in this case, we just use a single machine. If you see, we achieve results that in accuracy are comparable or even better than the others, but in times that are order of magnitudes better. So here only 55 seconds on one machine against minutes, hours on clusters. And it is, I mean, it is a pattern that you can see in almost all the experiments we've done. So million song, it is on the order of 1 million, the help, TMIT, order of 1 million too. We did, so SUSY, it is still high energy physics dataset, Higgs, you have seen it before. We did it even on ImageNet. The interesting thing here, okay, so here we don't put anything because we don't have results, we didn't find in their papers, sorry. We didn't find in their papers times on this for ImageNet. The interesting thing is that you can run it in only 4 hours on your desktop. And so what we did here is that we used the features from Inception V4. Okay, so we took the convolutional part of Inception V4 and to produce a good feature for the images, and then we applied Falkon on it, and you see that you achieve essentially the same accuracy. So it means, for example, if you want to do transfer learning, it could be a good way to try or to go. Okay, so the take-home message is that you can achieve, you can have optimal statistical properties on large-scale data sets with a computational complexity that is n in space and n square root of n in time. Okay. And the algorithm, as I said, is a combination of random projection, iterative solvers, and preconditioning. We have the result for the fast rates, and even for the adaptive sampling, so leverage scores, but I didn't present it here. What can we do next? So we have seen our algorithm relies on matrix vector multiplication, so in a parallel scenario, so in a parallel architecture, it works rather well. It is not clear how to distribute it. If you want to do on million machine over internet, it is not clear how to do it. And then the next step would be just to open, is a more scientific question, how to open the kernel black box to work maybe more with the important feature from it. So, thank you very much.
Any questions?
You have this probability 1 minus delta,
Mm-hmm.
but it is not with respect to the original measure, because you introduce randomization.
Exactly. It is with respect to the so it is respect to if you want both things. So if you can do the tensor measure, and then it is with respect to that one, because we have the probability on the data now and on the choice of the random features.
Yes,
The next point.
Randomization that you introduce,
Mm-hmm.
the low bounds are proved without randomization.
Exactly.
It is something like bootstrap setting.
Mm-hmm.
you are using. So in fact, this lower bound do not entail that with your randomization it will be optimal. So when you say it is optimal, you cannot refer to this bound, because to prove in your case, you need to condition on all the sample,
Mm-hmm.
and to take probability conditionally on all the sample of excess, and get a lower bound for this. And this is not given by Caponetto and Vito.
No, exactly. It is not given by Caponetto de Vito because they don't have to sample the Nystrom points in this case. Exactly. It is the lower bound under the assumptions we have seen before. But since it is minimax lower bound, it works for any algorithm that has an output in Hilbert space. So ours too works that way.
My point is that you have to prove the lower bound for your setting in order to say that it is optimal.
I don't know if I understand well the question. If you want, we can expand it offline. Another question?
Well, if not, maybe let's thank Alessandro again.
Okay, thank you.